Okay, in the last lecture we stopped in here, right? We stopped in here. Now we'll go start from this 123. I think this is a problem. We'll design the problem. So the determine the surface area of a settling tank for the city of Richmond, that is zero point 0.5 meter cube per second design flow, using the design flow rate of 32.2 meter cube per day per meter square. Compare this surface area with that which results from assuming a typical conservative flow rate of 20 overflow rate of 20 meter cube per day per meter square. Find the depth of the clarifier for the overflow rate of 32.5 meter cube per day per meter square, and detention time 95 minutes per length with ratio 4.5:1, and the maximum length is 100 meter, maximum depth is 5 meter. Provide minimum 2 tanks. So this is the problem. You guys can go ahead and read it. We should be able to solve it. I have a solution in the next slides. So here is the one that I solved here. So I have a Q value is given 0.5. So what I did here, so I converted into meter cube per day. So the overflow rate B equal to this, and for the purpose of conservative B equal to 20. Detention time T equal to 95 minutes. L max is this, D max is 5. L is to W ratio is 4.5 is to 1. Number of tank is equal to 2. So these are the data, right? Now we'll do the solution. So this is my solution. Settling to surface area. Surface area is equal to Q over overflow rate. Why? Because meter cube per day plus meter cube, this is meter per day ultimately. Day cancel out. Meter square meter would be remaining meter square. So I got 1329 meter square would be surface area. Total surface area for both of them, right? Both of them total surface area. Surface area for conservative B overflow rate is 2160. How much more we are providing? Looks like we are providing more, 62.5% more higher than this one. So this is a Michigan rule. I think Michigan they use 20. I think this is their thumb rule. It's not universal, but anyway, I mean in USA, Michigan. So, but 1329 is the best option because 32.5 is the things that we are looking for. The design surface area for the tank is would be this. Okay, so the volume of the tank V equal to Q times T. So then Q and T, we have to do a little bit of what is called the unit thing here. The second, 60 second equal to 1 minute, second cancel out, minute cancel out. Whatever it stays here is meter cube. That means it's 2850 meter cube is my volume of the tank. Okay, then tank depth would be volume over surface area. So I get 2.14. This is the depth for both the tank, and this is the volume for both the tank. It's just not for one, and surface area for both the tank. So the surface area for each tank, since I'm providing 2 tanks, would be 664.5. Now surface area would be L is to W. So L is to W, L is to 4 is equal to what? L is to W equal to 4.5. That means L is equal to 4 times W. So L equal to 4 times W. If you do 4.5 times W, so then W times 4.5 W would be 4.5 W square is equal to this. Then W equal to square root of 664.5 divided by 4.5, ultimately 12.15 meter. This is my width of the tank. Okay, the length would be 4.5 times W is equal to 54.68 is less than L max. Okay, less than L max. So, and also we calculated the depth. It came out 2.14, whereas maximum depth was 5. So definitely this is less than uh, D max, so it is okay. So both of them okay. The dimension of each tank, 2 tank, that we're providing 54.68 meter length, width is 12.15, and length is 2.15. Plus freeboard, we have to add some freeboard plus depth. If the L max requirement is not met, increase the number of tanks and recalculate the L and W. So in this case, 2 tank are already given anyway. So if 2 tank, it says minimum, and it took it. So if we could not get the L max L less than L max, then we have to increase the number of tanks. Can go 3, 4, 5, and continue until you solve the problem. So this is another problem. You are asked to design a water treatment plant settling tank length with depth and check for the volume provided after calculation for the CD of hostile. The design flow is 0.85. Overflow rate is overflow rate and detention time from the column test are found 35 meter per day and 94.5 minutes respectively. The city of still is asking to keep the length width ratio is 50, meter length width ratio is 4:1. So this is the problem, right? This is Lmax, this is L is to W, this is the T detention time, and this is the V0 overflow rate, and this is the Q, right? That's the only few things that I need. 1, 2, 3, 4, 5. Okay, so I use the Excel spreadsheet to do that. The other one I did by hand. Looks like Q equal to this, overflow rate is this, and this I calculated this one would be 73,440 meter cube per day. Detention time L max is 50 and ratio is 4:1, L equal to 4W. So surface area, first thing, calculate the surface area. We got 98.29 meters square. Then the volume required would be Q times T. So this is Q, T, and we have to convert those. We get 4819.5. And depth would be V over surface area, volume over surface area. The volume is my surface area. I got 2.3 plus sludge depth and freeboard. We have to add it with it. A freeboard is basically 6 to 12 inch, certain cases 18 inch also. Okay, and the sludge depth, if I know the volume of the sludge we are generating, then we know the surface area of the tank, then we'll come back, we can get the depth of the sludge. Okay, so then we'll see whether length to width ratio. So in this case, number of tanks is equal to 1. Okay, and the depth we got 2.3, the liquid depth, we are not using anything else. So my surface area of each tank A would be volume over D, right? Depth times number of tank. So in this case, 4819 divided by 2.3, I get 2098. This is my surface area for one tank. Then if I calculate the L is to W ratio, L got this, sorry, W is 22.9, L is 91.61. So it looks like L max is not okay. Change the number of tank to 8. How I come up with it? I did a simple equation over here. To come up with, looks like it was 7 point something, but I did 8. So, but you can do trial and error. You can go for 2, 3, 4, 5, 6, 7, 8. You have to keep doing until it goes and makes a sense to it. So if I use 8, then the surface area of each tank is volume divided by 2.3 is the depth of each tank times number of tank is that much. Then W would be equal to 8.1 and the L would be 4.5 times this would be 32. Okay, I think it's 4.0, not 4.5, right? It was 4.0. Yeah, 4.0. So this is not right. This is a misrepresentation, but here it is okay. So, okay. Okay, the volume provided would be the length, width, and the depth, and the number of tank, right? So this is length, width, and depth. It didn't show up here. It would be 2.3. So I don't know. It's not showing up over here, but the B total would be the same as is okay. So in practice, even number of tanks are provided. In this case, provide 8 tanks. If the number is odd, add 1 more tank. It's a kind of suggestion. It's not required. I have seen odd number of tank in different places. It's not a big deal. Filtration, the next step is once the sedimentation is done, then it goes to the filtration. Water leaving the sedimentation goes to filtration. Filtration is basically different types of filtration we can use based on the type of media we used. You can use dual media, coal and sand, and mixed media, coal, sand, and garnet, all of those. So the classification of filters based on the allowable loading. The loading rate is whatever the surface area flow rate divided by surface area will give you the loading rate, how much is going per unit area. So velocity means loading rate is meter cube per day per meter square. Ultimately overflow rate over there that we saw. Okay, based on the loading rate, the filters are classified as slow sand filter, rapid sand filter, or high rates sand filter. Here is the little details of the slow sand filter. This is the main loading rate, 2.9 to this. And there are some other things over there that you guys can read it. Rapid sand filter basically RFSFF is graded, layered in different cases. I'll show you some picture how the soil distribution goes there, here and there. And this one definitely we have to do the rapid sand filter are clean in place by forcing the backwater through the sand, called the backwashing. Okay, here is the loading rate 120 to 235 meter cube per day per meter square. Normally minimum 2 filters are required. For larger plants greater than 2 meter cube per second, minimum 4 filters. Maximum surface area per filter is looks like 100 meter square. So it could be 10 meter by 10 meter, or it could be circular, right? Whatever the diameter comes out to be. So this is one of them showing its empty one. These are called trap. Trap means when they do the backwash, then the water comes to the top. Trap gets the bad water. So I think most of the time, if you go to the water treatment plant, then you should see those when they are doing the backwashing and other things like that. So more picture. These are the trap. As I said, the trap water goes there and take more. So this is the backwash. So that means this is the filters sand filter, right? So when they do the backwash, then they open it and then the water goes inside from there. Okay, then agitate those, then the remaining water they use the trap and goes back to there. So this is the sludge lagoon. Therefore sometimes we use for the sludge over there. After the treatment, the sludge directly goes there and stays there whatever the number of days needs to stay for like say dewatering and other things. More of those sludge lagoons. Okay, dual media filters. Dual media filters remove larger particles on the top, smaller particles on the bottom, and complete the different layer. Coarse coal on the top and layer in the fine sand. So the loading rate looks like would be 300 meter cube per day per meter square. So and deep bed filter media came in 1980, designed to achieve higher loading rate of the 800 even, right? And consist of like 1.0 to 1.5 millimeter diameter anthracite. About this is the filter consists of millimeter diameters about 1.5 to 2.5 meter deep. So 1.5 means it almost 5 feet, right? Things like that. Here is the grain size distribution for the sand that we use in there. For silica sand, effective size D10 is 0.35 to 0.55. You may not understand that right now, but if you have taken geotechnical engineering, you'll see that we use all the sand distribution over there, here and there. Uniformity coefficient D60 over D10 is 1.3 to 1.7. So this is the distribution should be showing like that. Okay, so meaning, so this is the grain size distribution. Here it is D10 found here, D60 found here from this one. D10 means 10% passing, and if we do it, like say it would be whatever 10% will come here. So that means this is the size 0.19 because this is 0.2, here it is 0.19. Is this way, as right to left. Then 60, if it is 60, come here, then go here. Sorry, it would be okay. So this is the amount. This would be 0.1, 0.2, 0.3, 0.4. So it would be 0.45. So, and uniformity coefficient is 2.368. For this distribution, it looks like it is more than whatever required. So then we have to change it. We may not be able to use this one because it doesn't meet the U coefficient, uniformity coefficient, the range that we have. So this sand may not be good. Here is the calculate the hydraulic pressure loss. In this case, Ross equation is this. So air loss means this is a VAD, CD is the drag coefficient. You remember that F is the mass fraction sand particles of diameter. In diameter is in D. Mass fraction of sand particles of diameter. In different cases, you should be able to find it. And phi is the shape factor. Shape factor for sand. You guys will geotechnical engineering will give you a lot of idea on that. And N is the porosity of the materials. Okay, CD is the drag coefficient, D is the depth of the filter media, filter bed, filter sand, V is the approach velocity, HL is the friction head loss through the filter in meter. So if the initial head loss excess of 0.6 meter indicate that either the loading rate is too high or the sand has large fine grain material. That means flow rate is not going. So in this case, we may have to change it, design it, redesign it, and things like that. Okay, so we are going to stop here in this case.